Welcome to Chapter 9, Alkynes. Okay, so please follow along on the handout so you can see the names of these compounds. We want to write the structural formulas for ethyl isopentyl acetylene. So this is a common name. Acetylene would be the carbon triple bond. And then one side is going to be an ethyl, so we'll just write CH3, CH2. And the other side of the acetylene is an isopentyl. So isopentyl has 5 carbons, and remember it makes that Y looking structure. So then I would count 1, 2, 3, 4, 5. Okay, so that's ethyl isopentyl acetylene. B is cyclohexyl, so that's cyclohexyl. There's your cyclohexyl constituent, acetylene. So that should just be that right there. See, now it looks like we have, I see an E, which means trans, and there's the EN for the carbon-carbon double bond. We'll draw that. And then we have the 4-ine. So this is 2, so 3, 4, ine. There's 4, 5. Looks like we need 8 carbons because of the oct. So let's draw another carbon here. That's 1, 2, 3, 4, 5, 6, 7, 8. And then we go to ethyl. Ethyl is on the 6, so we'll go CH2, CH3 for that substituent. And then we have trans, so that means a hydrogen on top and a hydrogen on bottom. And then we can fill in CH3, 1, 2, 3, 4, 4, 4, because you know carbon likes 4 bonds. 1, 2, CH, CH2, and CH3. And there you go. And then we go to the last one, D. We have 5 carbons, 1, 2, 3, 4, 5. And on the 4th carbon we have the ine, so that's the carbon triple bond. And then on 1 we have the double bond, pentene. There's the ene, 1's the ene. And then on 3 we have a methyl. And we also have an S. So let's go ahead and write CH2 there. Notice we don't have an E or a Z there because this CH2 makes it so it's not cis and trans isomers. And then we're going to make this an H. That's a proton. Okay, so here we're all good except we're going to have a hydrogen here. And now we got to figure out which one goes forward and which one goes backwards. So this carbon is connected to 3 other carbons, so that's going to be your higher priority. If you add carbon connected to 3 carbons by your RS rule, naming rules, this would be a 2, and then the methyl would be 3. So we're going, that would be clockwise if the hydrogen's in back. That's an R. So we don't want that to be in back, so we're going to make hydrogen come forward. And then we're going to make this go backwards. So now you do 1, 2, 3, and it's R, but because of the backwards rule, it's an S. Okay, so now we are, I just turned my volume down, so I listened to the last one, it seems a little loud. Now you want to draw the IUPAC names for each of these. So IUPAC names is not the common names. And so what I do is I number 1, 2, 3, 4, 5. So my longest chain is 5 carbons, and I go ahead and write pent, and then it's going to be on carbon number 2. You can put a 2 right here, or you can put it before, whatever you prefer. And then on 4, your substituent is a phenyl, so 4-phenyl 10-ine. Our second compound is B, and B is 1, 2, 3, 4, 5, 6, 7. So we have 2 ene, we have 4 ine, and that's hept, and we have a substituent methyl on the 3. So that is 3-methyl. And we also have to consider, since we have an ene, whether we have cis or trans, and since you have a hydrogen and a methyl, and they're different, and then we have a methyl, and we have this group, and they're different. Because you look at what's on that carbon, and then what's on that carbon. Between the methyl and the hydrogen, this has a higher priority, higher molecular mass, atomic number, and between the methyl and this group, this one does. And you see that these are on opposite ends, so that would be trans. Trans is E. Okay, C. This is an alcohol. Alcohols have a higher priority. They have to be part of the chain, so we're going to give that the lower number. And we have then 4 ine. We have 3 all, and we have 6 in our chain, so that's hex. And we have a methyl substituent on 3, 3-methyl, hex, 4 ine, 3 all. Okay, D, we have, this is our chain, and the cyclopentyl is a substituent. We're going to give that the lowest numbering, so we're going to number it from like that. And so that is bu 2-ine, and on number 1 you have cyclopentyl. That is your problem for D. Okay, so I had some technical difficulties, so I've already worked all these problems, and then I don't know what happened to the volume. So this is problem number 3, and we're into the reactions. And this is devastating because, like I said, I already spent 45 minutes talking. Okay, we're going to start all over. And it says predict the products of the reaction with 1 pentyne. So we have 1, 2, 3, 4, 5. That's 1 pentyne. A lot of times I'll draw these just like this. 1, 2, 3, 4, 5. It's very important that you draw that terminal hydrogen. And the first thing we want to write the mechanism with 1 equivalent of HCl. So this alkyne nucleophile will then, I like to do my plus minus, will go after the electrophilic hydrogen, and then those electrons will go to chlorine. And chlorine will become a good nucleophile at that point because it has electrons with a negative charge. And what you have then is the addition of a hydrogen, and the hydrogen is going to go to the terminal carbon to give you the positive carbon. This carbon here is a positive. Now this is an sp2 carbon, so you can imagine it has an unhybridized p orbital, and that's a great electrophile. So these electrons then will go from the nucleophile. Remember, we go from the nucleophile to the electrophile. So the electrons go and fill that orbit, and you get a vinyl chloride with 1 equivalent. Now, if you add the second equivalent, so a second equivalent of HCl, once again, there's your plus and there's your minus, that's your dipole, and you have the pi bond electrons are nucleophilic. They're going to attack the hydrogen electrophile, and those electrons are going to go towards the chlorine. So the same thing happens here. Chlorine nucleophile. And then when you redraw this, that hydrogen once again goes to the least substituted carbon to generate the more stable carbocation. This is Markovnikov's rule. And then your chlorine will go nucleophilically attack the carbon, and what you end up getting is a geminal. It's called a geminal dihalide. Okay, so the next problem is reacting the 1-pentyne with excess hydrogen and nickel. Now this goes to the alkane. So 1, 2, 3, 4, 5. This is pentane. Okay, easy does it. The next reaction, though, with 1-pentyne uses a poisoned palladium. So barium sulfate poisons the palladium, and a little bit of quinoline also does. And with the excess hydrogen now, so here your metal, palladium, has its hydrogen in the metal, but it's only going to deliver 2 hydrogens. And because of the way it'll deliver it syn on the same side. We'll go ahead and draw that hydrogen in there. And in this case, it doesn't matter because we don't have trans or cis, because those hydrogens on this carbon are the same. They're both hydrogen. But just so you know, that does stop at the alkene, and you have 1-pentene as your product. Okay, the next reaction, we have bromine, and we're going to add 1 equivalent, or 1 mole of bromine. Now remember what I said in class, this is like a delta positive and a delta minus. It kind of polarizes. And now your nucleophile, your alkyne electrons, will go after the electrophilic bromine, and then those electrons in that bond will go towards the bromine. And what you get, you can imagine, is kind of like almost like a bromonium. And you have now a bromine nucleophile, and this bromine nucleophile will come in and attack the carbon, and you get a vinyl dibromide compound. The next question asks for 2 equivalents. So if we add a second equivalence of bromine. Well, this is alkene chemistry, right? In chapter 8, this is a delta positive and delta minus. And once again, your nucleophile is your alkene that goes after your delta positive bromine. Those electrons go with bromine to give you a nucleophile, and the bromonium ion, which is the 3-membered 1, 2, 3, 4, 5. This 3-membered ring. Now your nucleophile comes and can attack the carbon. And when this happens, you open that ring to form a tetrabromide. And this is your substrate for actually making an alkyne using those strong bases. Okay, the next reaction uses cold dilute potassium permanganate. Now, hopefully you remember that with alkene, that oxidizing agent with alkenes make a diol. In this case, you're going to make a ketone and then a carboxylic acid. And so this is 1, 2, 3, 4, 5, and that's 2 keto. That's 2 keto pentanoic acid. Pentanoic acid. Now, what if you use warm potassium permanganate and some base? What you're going to get is a thing called oxidative cleavage. And so what happens is here it's going to cleave, and this will cleave to the carboxylic acid, except you're in base, so it will lose the proton to make a sodium salt. And then the terminal CO2 will fully oxidize to carbon dioxide. This is the fully oxidized carbon because carbon's bonded 4 times to oxygen. And remember that carbon does 4 bonds. The next reaction is entyne with sodium and liquid ammonia. Now separate these two because what's happening is, remember in class we talked about the sodium and liquid ammonia gives you the blue free solvated electron, and this electron is going to add to the carbon, and then you get this intermediate. Okay, so you have a free radical and you have an anion, a vinyl anion, and now you have ammonia in solution because that's the liquid. So you have liquid ammonia, and then the nucleophile here, the carbon anion, will come and take a hydrogen away from ammonia, and that becomes NH2, and that will go and get another ammonia. They're kind of like in equilibrium. But what's happening to your alkyne now is that it has a free radical. So this is a radical, a vinyl radical. And another electron, this happens twice, still in solution, will come and bond there. And when that happens, now you have a carbon anion that will extract another hydrogen from the ammonia solvent, and you get an alkene. This is nice. You have an alkene, and this is actually a transalkene, but in this case, because both of these are terminal and the hydrogens are at the end, you wouldn't see that. You wouldn't call that a trans, like an E, because it doesn't have cis-trans isomerization, but you would see that if it was an internal. But this is a nice way to stop the reduction at an alkene stage, and it's trans, which is opposite of the quinoline, Lindlar's catalyst that we just saw. Okay, and the last two problems on this sheet for this problem uses mercury sulfate, water, and sulfuric acid. So the key here with alkyne is, well, one, you want to think of the mercury as a big fat proton. So there's your big fat proton, and then you get this vinyl carbocation. It's a vinyl carbocation. This follows Markovnikov's rule because you want the most stable. And your water is your nucleophile. Those electrons will go into this sp2, this p unhybridized orbital, nice electrophile. And what happens is then, let's just go ahead and put the OH there. And then the mercury, after the sulfuric acid protonates it, and because you're going to get reprotonation here, and then the mercury leaves. The goal here then is to generate your enol. So this is your enol. That's your intermediate. And you're going to do Enol Tautomerization, the enol for the carbon-carbon double bond, the OH for the OL, all. And the way I do this is I just take those electrons, I do kind of an internal where it takes the hydrogen, and these electrons come down to form a carbonyl. And then when you redraw that, there's your carbonyl, and there, like that. There's your hydrogen there, and your hydrogen there. This is a ketone. So we went from an alkyne to a ketone, and this is a 2-keto pentane. Oh, no, you wouldn't want to do that. You want to call it a pentan 2-one. That's what you want to do. Okay. And then the next one you have is a reduction. So you have borane reagent, and then you have H2O2 and base. Now, this is sec 1, 2, 3, 4, 5. So this basically adds on boron twice. It's just a sterically hindered way to make sure the boron only adds one time to your alkyne. And the hydrogen's going to add to one of these carbons, and it's going to add to this carbon here. And the reason why it's going to add to that carbon is because the boron wants to add to the sterically less hindered carbon. So this carbon is going to get the hydrogen, and you're going to get a double bond here. And then this carbon is going to get the boron. Now, when this happens, they're going to add on the same side. This is syn addition, same side. Now, what's going to happen is boron is going to get oxidized. Hydrogen peroxide is an oxidizing reagent, so we're going to replace the boron with an OH. And at this point, you need to recognize that this is an enol, and the enols will undergo tautomerization. And so this hydrogen gets taken from this, and then those electrons will go here and form a carbonyl. And so when you draw this, one, two, three, 4, 5, you get 1 pentanal. See, that's Al. Al, not Ol. Ol is alcohol. Al is aldehyde. It's an aldehyde from the alkyne. Okay, on this problem we are accomplishing synthetic transformations to show all intermediates. So we're given our starting material and then the desired product, and we have to come up with the reagents. So let's draw the first for A. Butane, 1, 2, 3, 4, and 2-dibromo. And we want to go to 1-butyne. Now, I don't like the way I drew that because it doesn't show that the alkyne is linear. So we're going to draw this again. 1, 2, 3. So 1, 2, 3, 4. So there's 1-butyne. Since it's a terminal alkyne, the best reagent would be sodium amide, which is a strong base, and about 150 degrees. And the terminal amide will get deprotonated. Okay, so let's go to the next one. Same starting material, 2-dibromobutane to an internal. So now it's 1, 2, 1, 2, 3, 4. Okay, butane. So if it's an internal, you want to do the other base that we learned, which is potassium hydroxide, and they call this fused, and it's at 200 degrees Celsius. Like I said, I've never done these two reactions because I just usually order my alkyne, but if you need to do it, it's tough. It gives the most stable, these conditions give you a stable internal alkyne. So just know when to use the difference. All right, so the next transformation is C, and we are going from 1-butyne, 1, 2, 3, 1-butyne, and we want to go to 3-octyne. 1, 2, 3, let's see, once again. Okay, 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4, 5, 6, 7, 8. Now, can you see that this 1, 2, 3 is this 1, 2, 3? Can you see that? So we're at this carbon here. We can make that a negative carbon, and we use sodium amide. Okay, so sodium amide is going to deprotonate that and make that a negative carbon nucleophile. And then we have to react it with 1, 2, 3, 4. So 1, 2, 3, 4. So this is carbon number 8, 7, 6, 5. And we want that to be a primary halide, alkyl halide. Preferably like something like bromine. Okay? So you can write CH2, 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 CH3. And what's going to happen there is the nucleophile does an SN2 reaction, and you get your desired product. All right. The next, I'm just going to put that up there. The next reaction is D, and we're doing trans 2-hexene. So this, 1, 2, 3, 4, 5, 6. On the 2, we have an alkene, and we want it to be trans, so I'll put the hydrogen up here and hydrogen down here. Okay, so that's our starting material. And let's see what it wants us to make. It wants us to make 2-hexyne. All right. So we want to make 1, 2, 3, 4, 5, 6. All right. So how do you go from an alkene to an alkyne? Well, the first thing you're going to have to do is you're going to have to add bromine. And that's going to brominate. And if you remember, we showed the intermediate there. It makes the dibromine. We actually add anti because it makes the bromonium ion, chapter 8. And once we get this dibromide, then we can add a strong base. And just like we did up here in B, problem B, we're going to use KOH, 200 degrees Celsius, fuse KOH, and that will make, that's an internal alkyne. So that should work. Okay. Now we are on cyclo. Move that all the way up. Really take that off the page. All right. Cyclo. Okay. Design. Now, a little trick to making these 10 cyclocarbon. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 10. And we'll put an alkyne. Not going to be drawn exactly right, but there we go. And we want to make cis cyclodecene. So that's 10. So I'm going to draw it like that, and we want to make this, and we want to make it cis. So that means a hydrogen here and a hydrogen there. And we just put it that way even though it doesn't look like that in our drawing. So basically, what are we doing? We're doing a reduction from an alkyne to a cis alkene. There's one way that we know to do that, and that's Lindlar's catalyst. So do you remember a Lindlar's catalyst? It's palladium poisoned with barium sulfate and quinoline. And then you gotta have hydrogen. Don't forget the hydrogen. The hydrogen is what actually adds to the alkyne. All right, this one we don't have our subscripts, so we'll figure that. But it says 2-hexanone. So let's just go ahead and draw that. 1, 2, 3. Okay, so is that 1, 2, 3, 4, 5, 6? So that's 1 hexine, and we want to make 2-hexanone. Does anybody know how you're going to do this? 2-hexanone. You have one way, one reagent that you know, and that is the mercury sulfate, or water, okay, to make your vinyl cation, and then sulfuric acid. And that will make the enol. The enol tautomerizes to the ketone. Okay, and the last one is, we'll write it down. We want to go from a trans, 1, 2, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, trans 2-hexene to a cis. So, let's see. 1, 2, 3, 4, 5, 6. So we want to go to 6, 2-hexene. And the way that I know how to do this is to go to the alkyne. Let me just double check. I don't know. Okay. I was saying I don't know because I don't know where I was in my notes. Okay, so what I think you need to do is add bromine first, and then 2, since it's internal, do KOH, 200 degrees, diffuse KOH, and then the third thing you'll want to do is reduce it using Lindlar's catalyst. All right. Okay, so problem 9.5, how would you synthesize compounds from acetylene? Okay, so you might not see that, but you should see that on your paper. Acetylene is acetylene. It's a generic name for ethyne and other needed reagents. So the first one, A, is the first thing you have to do is you need to draw it. So it is 6-phenyl. So here's your 6 carbon. Phenyl hex 1-ine. So you got 4-ine. So this is 5, 4. There's 4-ine. And you don't have anything at the 2. But you have 1. There's 3. Let's just go ahead and draw 2, 1. 1, 2, 3. And at 1 you have an E. So this is H2. This is H. And this is H2. Okay, so how do you make this from Helen? Well, here you have your acetylene. And so the first thing you're going to do is you're going to have to bring in one group, and then you can bring in the second group. So the way you do that is you add one equivalent of sodium amide to make your carbon nucleophile. And one equivalent, and then you react this with, you do an SN2 with benzyl bromide, CH2Br. So basically, there's an SN2 and you get CH2, C, and then your alkyne there. And then you do this again with sodium amide, and you're going to deprotonate that again to make a carbon nucleophile. And now you're going to react it with this other portion, which is CH2, CH, and then CH2, and we're going to throw a bromine on there. And what is that? That's an allylic bromide. This will go in SN2 because notice the bromine is connected to an sp2 carbon. But this allylic, with this carbon-carbon double bond, makes it even more reactive than a primary. So it will do an SN2 reaction, and then you have your product. And we'll just write product for time's sake. Okay, the next problem, using the same starting material, you want to make cis 1-phenyl 2-pentene. Okay, so I'm going to look at my sheet now and then draw this. So first thing you have to do is draw the desired product. So what's the desired product? 1, 2, 3, 4, 5, because that's your pent. 2, you have the ene. 1, you have the phenyl. 1 phenyl cis, so you have hydrogen on both sides, and 2-pentene. So this is CH, that's CH2, CH3, and you want to make this from the alkyne. Okay, well, you want to add the same reagents here. So you're going to do what you did before with one equivalent of sodium amide, and then you're going to add your phenyl benzyl bromide. This is going to do an SN2, and then you're going to be given the same substrate here. Okay, now then you're going to want to add on the ethyl. So you'll do another equivalent of sodium amide and a ethyl bromide. This should be a 2. And then that gives you this compound, alkyne. And at this point, you need to reduce this, and you reduce it to the cis. So you want to use hydrogen, palladium, barium sulfate, and quinoline. Okay, so quinoline, hydrogen gas will give you, and for time's sake, once again, your time and mine, I'm not going to draw it, I'm just going to say, will give you the desired product right here. Okay, using the same starting material, the alkyne, we're now going to try to make the trans. So the same exact product except trans. When you come down to the last step, instead of using the quinoline Lindlar's catalyst, like you did in the last step, don't do that. Use sodium metal in liquid nitrogen. Okay, sodium metal and liquid nitrogen, and that'll give you the trans product. Okay, the next problem gives you a Fisher projection, and it looks like it wants the diol. So let's just look at what this is. This right here can come from your alkyne portion. So you're going to do the same step as you did before, where you take your alkyne, react it with sodium amide, and then react it with the benzyl bromide. Okay, so sodium amide, and then that's going to add that portion to that carbon. It's going to be this carbon. And then you're going to do the same thing, another equivalent of sodium amide with ethyl bromide, and then that's going to connect it to this carbon. Now what you're going to have then is you're going to have CH2 phenyl carbon, your alkyne, and CH2 CH3. Now, can you think of a way you can get a diol? If you reduce this down, and it's on the same side, this is cis, so you need to reduce this cis. So let's do Lindlar's catalyst. And then you can get CH2 phenyl, C, you can get the cis, CH2, CH3, and then how do you make a diol? Cold, neutral, potassium permanganate, and that, or you could do osmium tetroxide. This is, and it should give you the cis OH, and that is your product. And let me see my notes to see if I did the same stuff here. Yes, you could use osmium tetroxide and hydrogen peroxide, or you could just use cold potassium permanganate, both oxidizing agents. Okay, now we're on problem 9.6. Predict the product's form when, so let's rewrite this. CH3, CH2, acetylide that are lone pair. This is a nice strong nucleophile, reacts with ethyl bromide. Okay, so ethyl bromide, this is a primary alkyl halide, does an SN2, you get displacement, CH2, CH3, you elong the chain. What about tert-butyl bromide? Tert-butyl bromide, well, that's a tertiary alkyl halide. It's not going to react like that. It's going to act as a base. And so you have hydrogens here that this nucleophile right here will extract a hydrogen and you will get elimination, E2. So what happens then is this. Okay, and the other product then would just be protonated alkyne. So, because there's the hydrogen. All right, so where are we at then? Formaldehyde. What is formaldehyde? It is the simplest aldehyde. So here's formaldehyde, and the nucleophilic carbon then will come and attack the carbonyl. Remember, the carbonyl is slightly positive and the oxygen's negative. So when it attacks the carbon can only have 4 bonds here. So these electrons go up to the oxygen, and what we get is CH2, the nucleophilic carbon attacks this carbon, which is this carbon here, and then we have O, oxygen negative, and this is a hydrogen, and this is a hydrogen. And then what happens that they don't show you is then you would quench this with acid and you would make an alcohol. And you can go ahead and draw that alcohol in. I will do that. CH2OH. Okay, what if it reacts with cyclohexanol? Cyclohexanol. That would be cyclohexanol. Once again, draw your delta positive. This is your carbon that's positive and delta negative. And your nucleophilic carbon then will come and attack this carbonyl carbon. And you will get an alkoxide. This carbon is 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4. And then once again, you would quench this with acid and you would have an alcohol, an alkynyl alcohol. Okay, that's this one. The next one looks like an aldehyde. CH3, CH2, CH2, and then CHO is the aldehyde. So here we have our nucleophilic carbon. Attacks the delta positive carbon of the carbonyl, and those electrons go up, and then you form a carbon-carbon bond. And this would have a hydrogen there, that's the hydrogen, and then your chain here comes in here. And then of course you would quench that, which I will go ahead and just erase it for time's sake, and put an OH. So there's your alcohol, alkynyl alcohol. Okay, what about with cyclohexanol? Let me actually just do it all. Cyclohexanol. Well, what happens? Well, this is gonna, you gotta recognize that's an acidic proton. Get your pKa table out, and you'll see that that's the pKa between 16 and 18. And now you have your alkyne. And so what happens here? Let's just leave this blank, as we'll try to figure out what's the reaction arrow. And if this actually takes that acidic proton, what does that product look like? Okay, so on the other side of the reaction arrow, you get something that looks like this, where this is your proton, and now it's over here. And we already said that this pKa of that proton there is 16 to 18. And the pKa of this proton here is about 25, right? Because that's your alkyne. So the equilibrium lies to the weaker acid, which is the larger pKa value. So it's going to act as a base and deprotonate. And the last one on this problem is 2-butanone. 1, 2. There's 2-butanone. And once again, this alkyne will attack the delta positive carbonyl and open that up, and you get, and then you can imagine acid and alcohol. So we'll just go ahead and draw that in, and you get an alkynyl alcohol. Okay, the next problem, 9.7. How would you synthesize the following carbons, starting with acetylene and the other carbons? All right, so let's see what we can do here. Acetylene is this right here. Looks like a problem we've already had. 2-hexyne. So you got to draw these out. Let's do 1-hexyne first. Not Ca, but it's 1-hexyne. Okay, so 1-hexyne. And there's 1, 2. So we need to add 4 carbons right here. So the first thing you're going to do is react it with sodium amide. And then the second thing you're going to do is react it with an alkyl halide. All right, what if you want to make 2-hexyne? Well, 2-hexyne is an internal. So 1, 2, 3, 4, 5, 6, and you're going to have to do this twice then, because you have to add the methyl, and then so you do the same thing you did there, and so then you can take your product and react it with another equivalent of sodium amide and CH3 iodomethane. That would be good. Okay, so, all right. So then the second one is cis-2-hexene. So, um, so go ahead with the 2-hexine that we made right here. And then to make cis, the cis is the key here. You just want to take that product and react it with Lindlar's catalyst. And for D, you'd want to take the 2-hexene, and you'd want to react, for D, you'd want to react with sodium metal and liquid ammonia. Okay? That's D. For E, 1,1-dibromohexane. So for 1,1-dibromohexane, 1,1-dibromo. Okay, so you're going to have to go with the hexine, and let's go back to this product here. We're going to go with the product of 1-hexine. So let's go back to that product, 2, 3, 4, 5, 6, and let's react it with bromine. And the bromine is going to react, actually, you'd want to actually take that down to your cis. So you can do Lindlar's catalyst, and then what's going to happen then is you're going to get CH2, CH2, and then you can react that with bromine. And when you act that with bromine, that's going to give you actually a 1,2. A 1,2. So let me see. 7E. Follow steps from 7A. Okay. And then you want to add HBr. So, okay, let's go back to, once I do that, I think it, okay. Okay, so you want to go back to this compound here. Let's go back to the very first one where we made our 1-hexine. Okay. And then we want to add HBr. So what if we add HBr? Now we wanted to go to the least substituted. So remember, you need to add the peroxide, right? And so what happens then is you're going to get the free radical and you will get the bromination on the 1. One, 2, 3, 4, 5, 6. Okay, so there you go for that one. And then for 7F, it asks for 2,2-dibromo. 2,2-dibromohexane. So what you want to do is you go the same starting material as the 1-hexine, and you add just HBr, and that's going to be Markovnikov's addition, and that'll give you the 2,2. Okay, so 7G is pentanal, and how would you synthesize this? Okay, so from acetylene. So let's go and look at this again. Now we got pentanal, so we need to keep the terminal alkyne because we're going to make an aldehyde. So what does pentanal look like? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So we have 1, 2. So we need to add 3, 4, 5. So how we're going to do this is just an SN2 with a primary alkyl halide and 1 equivalent of sodium amide. And then we have made 1 pentyne, 1, 2, 3, 4, 5. And then how do we make an aldehyde here? Remember we used this borane reagent, this sec-isoamyl borane, and then we have to oxidize that with hydrogen peroxide and sodium hydroxide. Through an Enol Tautomerization, you will end up getting your aldehyde. Okay, that's 7G to 7H, 2-pentanone. Okay, so here you want the same compound, except now the reagents are going to be mercury sulfate and water, and then follow with some acid. And this time when you get the enol, because it goes to the more stable carbocation Markovnikov addition, for your enol, you're going to tautomerize to your ketone. And that's going to give you 2-pentanone. What does 2-pentanone look like? 1, 2, 3, 4, 5. Okay, so now we're on 7I, and that's a plus minus, so that means it's racemic, 3,4-dibromohexane. So what does that look like? 1, 2, 3, 4, 5, 6. So dibromo, 3,4-dibromohexane. And you're going to have to make an eternal alkyne. So you're going to take your acetylene with sodium amide, and you're going to react it with CH3, CH2 bromide. So that's an ethyl bromide, and you'll do that 2 times. And then what happens is you'll get this alkyne. And then at that point, you want to add bromine. And bromine will, the first time it adds, will make actually, you don't want to add bromine at this stage because you need to reduce it. So, let's reduce that. So, to reduce that, you want to reduce its cis. So do Lindlar's catalyst. And that's going to reduce it to the alkene. And then you're going to add bromine. And that will give you your desired product. Okay, 7K. I think we went 7J. 7J. So 7J is meso 2,3-butene diol. So what does that look like? That looks like this compound. So first you extend the chain. So you do this by sodium amide NH2. So that's a 2. And iodomethane. And you do that 2 times. 1 time here and 1 time there. And then what you'll have is an alkyne 2-butane, basically. 2-butyne. And then you'll want to do Lindlar's catalyst. Lindlar's catalyst. And that's going to give you a cis alkene. And then from there, you can add osmium tetroxide and hydrogen peroxide. If you're not familiar with this, go back to chapter 8 with alkenes. And this will form a diol that's cis with an alkene. And that gives you your desired product. And then we're on 7K. 2-methyl hex 3-ine 2-ol. What does that look like? Let's draw that structure. And the first thing you want to do is from the alkyne, sodium amide, and let's add the ethyl. So CH2, CH bromide here. And then, this is going to be fun. Look at this. So what do you have here? Once you do these steps here, you make your alkyne and you lengthen your chain. So you have this now, this portion. You have an alcohol. So you can react this with sodium amide again, and that's going to deprotonate and make your carbon nucleophile. And to make an alcohol, you can react this with, this carbon comes from a carbonyl, acetone, CH3, CH3. You see the alcohol, you can also, that's tertiary alcohol. So the tertiary alcohol comes from the ketone. And so what do you have here? You have your product. Okay. 9.8. What is the structure of compound Z when a compound Z is treated with ozone, followed by dimethyl sulfide and washing with water? What's kind of interesting about this is your byproduct is also DMSO. DMSO. When we do reactions with DMSO, we call it the pig reaction because it smells. There's one of the oxygens that comes from ozone. So you got O3. So the different oxygens will do an oxidative cleavage, and you can actually identify where double and triple bonds come from. So you definitely want to review this, but this is we'll talk about this. Here's a double bond, CH3, CH2, and an alkyne. Now let's see if this works. Sometimes this is trial and error. Okay, if you have the carboxylic acid, so you did the cleavage. Okay, so here we have a ketone. So now the interesting thing about ozone does an oxidative cleavage, but it doesn't actually, it's not as harsh as like potassium permanganate, warm in basic conditions. Ozone will actually make the ketone and a carboxylic acid, and it can also make aldehydes. So this portion here came from an alkene because it's a ketone. This portion here came from an alkyne because it goes to the carboxylic acid. And this is a terminal alkyne. So here's a terminal alkyne, and then and what was that connected to? That was connected to another alkyne. So this carbon right here. So this is the blue carbon, and then actually you got the CH4 here. Wait a minute. So CH3, CH2. So this might be backwards here. You also have the carboxylic acid, and the carboxylic acid came from the terminal alkyne. alkyne. So this is an aldehyde. So yeah, I just drew this wrong on this paper. So this is your terminal alkyne. So we'll call that 1. And this would be 1. So there's your terminal alkyne. And then it's got to be connected to an alkyne. And the alkyne, this came from an alkyne. So this is your second alkyne. And then this is your CH2, it's your CH2. And then this came from an alkene. So there's your alkene. And there's your CH3. There's your CH3. And then this came from an alkene because it's an aldehyde. An aldehyde. So there's that one. We'll even put a little star by it. And then you've got 4 or 5 carbons. 4 or 5 carbons. Problem 9.9. Show how you convert the following starting materials into the target compound. You may use additional reagents you may need. So this is retrosynthetic chemistry. And what you want to do is you want to kind of see where you can break these. So you can make this, right? Where did that come from? You see that you could do that. And from a terminal alkyne. So there you go. You took the hydrogen away. Okay. And then an epoxide. Epoxide comes from an alkene, so this takes care of that. You're going to start with this. So the other thing you want to do is get a carbon-carbon double bond. And then your cyclo. So what do we have here? Okay, so basically what you want to do, they give you the reagents here. You react this with sodium amide, and that will make that compound there. And the first thing you want to do, go ahead and react it with the benzyl bromide because it has less functionality than an alcohol. And so you want to add your alcohol in last. Okay, that's the same thing as the phenyl group. So then you're going to react this with sodium amide again to generate your negative carbon species, and then you're going to react this with your cyclopentyl aldehyde, and you're going to generate an alcohol. And I'm not sure whether you would know the next reaction or not. So you quench that with acid. That would be a dehydration. So you can add sulfuric acid and heat, and that would make the alkene. And then you can react an alkene with MCPBA. So what does that look like? So I'm not sure if you've done the dehydration, but basically once you get an alkene, MCPBA, that's metachloro in chapter 4, metachloro perbenzoic acid, and it will make an epoxide, and that will give you your product. Okay, problem 910. These were pulled from old ACS exams. So you have 3 of them. So let's quickly think about how we would do this. Okay, so you got to recognize you have an alkyne, and you have to recognize these reagents give you a ketone. And so you look for a ketone. That's an aldehyde. That's an alcohol. That's an alcohol. So A is your answer. And you count carbons just to make sure. 1, 2, 3, 4. 1, 2, 3, 4. You're good. Okay, right here. Same reagents. Okay? This is mercury sulfate and sulfuric acid. And you're looking for a ketone. A diol is from potassium permanganate. here's a ketone, and here's a ketone. This is an alcohol. So you're down to 2. Let's look and see, will it matter where the ketone goes? In this one's kind of challenging because this would be resonance stable. So when you're making your enol, so what happens is when you get this intermediate with your mercury, this would be the most stable because it's benzylic. The benzylic position is a carbon next to a phenyl ring. So D would be the answer because that's where your water nucleophile will come in. It's the more stable carbocation. So D would be your main product. Okay, here, this is, we talked to, it's just a cyclohexyl borane, but you got to recognize borane. And then you're going to oxidize that. So this is a terminal alkyne, so you recognize that it makes an aldehyde. That's a ketone. This is an aldehyde. So the answer is C.